Hi, welcome to part one. So in part one, we're just focusing on learning how the program works and making sure that we're recording the data accurately. So part one, it says learning the program. You're going to open up the program in a new tab. So there's a link here. You're going to click that link. The program will load up for you. Okay, so basically it gives you the same directions or similar directions to those that we talked about in the background information video. So let's take a look at the simulation. So for part one, it gives you information, exact variables in which you need to plug in. A nice way to do this would be to move this to its own tab. Consolidate it. And have the other lab as split screen, so that you can toggle back and forth between the simulation and recording the data. Okay, in the video you can't actually see split screen, but that's okay. So I suggest that you use the split screen. It makes collecting the data a little bit easier. So when you're on the actual simulation, you're going to click Begin. I'm going to close out of my video so that you can see the simulation. So basically here for part one, it asks us to change Trevor's mass to 100 kilograms. So this toolbar here, you can increase by increments of 10, decrease by increments of 10, or if you want to go up and down by single digits, okay, you can use the arrows in between. So technically we want 100, so I'm gonna head to 80 and then up to 100. The spring constant we want to be 900, so I'm gonna go down by a few. So I have my mass. Trevor's mass will be 100 kilograms. The spring constant, the rigidness of the spring, will be 900 newtons per meter. Okay, again, this is a life-sized pinball machine, so that's a realistic mass for a person. In order to actually set the spring compression, you're going to have to click Set Trevor. When you click Set Trevor, it's going to zoom in. Okay, so it's going to zoom into Trevor, and here's this spring. So you want to compress it by 0.6 meters. So we start at 0 meters. We see that mark of 1 meter. We have 1, 2, 3, 4 divisions. So that means that each of these divisions are worth 0.2 meters each. Okay, so each division is worth 0.2 meters each. So if I want to compress it 0.6 meters, I'm going to have to move it back 0.2, 0.4, 0.6 meters. So I'll have to click pull back 3 times. When I'm ready to release, okay, so right now we have only elastic potential energy. When I'm ready to release, I'm going to click Fire Trevor. When Trevor is fired, all of that elastic potential energy will be converted to kinetic energy. So Trevor will gain velocity. We want to determine the velocity of Trevor. So we're going to time how long it takes for him to move through the neutral zone, which again was explained in the first video. Okay, so I'm going to fire Trevor. He's going to be sprung across the ice. Now his kinetic energy, as soon as his hands touch that blue line, I'm going to click Start Timer. And as soon as his hands hit that blue line again, I'm going to click Stop Timer. Okay, I'm now going to record that time. Okay, so his time was 10.12 seconds. So I'm going to head to my lab sheet. And under time, I'm going to type in 10.12. Okay, you do not need to include the units in the data table. The units are in the title. When you graph your data, you cannot have units in the actual data columns. You can only have them in the title. To find your speed, okay, in this case, it'd also be the velocity, but to find the speed, we know that speed is distance over time, okay? Or if you want to think about it in terms of velocity, in this case, they're the same thing because Trevor only moves in one direction. The velocity would be the change in the position over the time. And remember, we only measured the time in the neutral zone, so between these two blue barriers, which we know is 18 meters long. So to find the speed, I'm going to take 18 meters, divide by 10.12 seconds to find that speed. And we get 1.78 meters per second. So I'm going to go ahead and transfer that to my data table. So Trevor's speed is going to be 1.78. Okay, again, we don't put the units in the actual data table. You'll see a note there. When you repeat this yourself, okay, you want to practice timing and you want to stick to that timing practice throughout the entire lab. When you calculate speed, if your speed is not somewhere between 1.6 and 2 meters per second, you are doing something wrong. So if you're outside that range, you need to go back and check that the mass is correct, the spring constant is correct, and that the spring compression is correct. Okay, if you're having issues, feel free to contact me. Okay, but do not move on until you've confirmed that when you try this yourself, you get a value for speed that's somewhere in between 1.6 and 2. Do not verbatim copy my data, because then you will not know if you're doing the lab correctly until it's too late. Okay, so that is it for part 1. You can head to part 2 for the next video.